Welcome to the exciting quantum world. And I'm Taposh Roy, and today we are going to talk about quantum cryptography. We have with us Anna Naden. She's from the Quantum Physics Corporation. Um, Before we start, a high-level introduction about me. I am the director of innovation at a company called Kaiser Permanente. My work focuses on digital twin, long-term 3 to 5 year modeling these days for COVID, image processing, and data science architecture and strategy. Prior to KP, I was head of ad products in a couple of startups in Bay Area, California. Prior to that, I worked for a MIT-based consulting company uh, as a senior associate. I also co-founded a company, biotech company called Biointegrated Solutions. Interestingly, we did that in Chicago, and this is back in 2003, I think. Yeah. We made liquid handling devices. I'm the author of the book, Medical Image Processing with Deep Learning. I have graduate and postgraduate degrees from IIT in Chicago and then from UC Davis. And yeah, if you want to connect with me, I'm always open to be connected on LinkedIn. Just a tidbit, my interest in quantum computing, my PhD research was in device physics simulation. So I did a lot of groundwork and research back in the day, and I'm catching up right now. We have a volunteer. Her name is Divya. She is in middle school, and she's a Python programmer. She also is part of the Qubits by Qubits program for quantum computing, and she's helping me out with setting up feedbacks and other things. So thank you, Divya. With that, I'm going to quickly move towards Anna's talk. And before we do the talk, this is the agenda. We talk about quantum cryptography. We have a Q&A session, and then audience Q&A session. Anna will go through a couple of things here. So two principal applications. One is the QKT, making the public key, and the second will involve the requirements for the secure key distribution using photonics for quantum information processing. Anna's introduction, I mean, she is retired from software engineering and took up quantum physics, which is very interesting. She founded the Chicago's quantum computing meetup, and then later quantum computing with Anna. She hosts and organizes meetups with AWS. While she was young, Anna was involved in the physics PhD program and has earned a master's degree. So thank you, Anna. With that, Anna, I'm going to pass it on to you and stop sharing my screen.
Thank you, Taposh. So it's a battle of wits, right? You have the hackers are always trying to figure out a way to read the message, read our email, and we're always trying to figure out a way to keep them from doing it. And the most secure way, well, if you have an encryption, any encryption algorithm, you can use statistical methods to determine the key if you have enough computing power. Well, there's one exception. If the key is just as long as the message, then you can merely exclusively OR the key with the message. And that's called a one-time pad. And it's unbreakable. You simply can't, by statistical methods, determine the key because different keys correspond to different messages. The statistical approach to cryptanalysis is that you try to find the keys that produce messages that are intelligible, that are words. Well, with the one-time pad, where you have a key as long as the message, it means that any message, one key could translate the message to be attack at dawn, and another key would give a message retreat now, for example, and another one might say meet me at Denny's for hamburgers. I mean, any message can be accomplished. And so statistical methods don't work. But the problem is that you need a very long key. You need a key that's as long as the message. And you can only use it once. If you use it more than once, then statistical methods can be used to determine it. So to get this perfect security, this unbreakable security, that's why it's called a one-time pad, because you can only use it once. And so the problem is the two parties that are communicating, we call them Alice and Bob, have to share that key. So how does the key get from Alice to Bob?
Excuse me, Anna, are you sharing slides?
Yes, I will.
Okay.
But that's the problem. Key distribution. And because an eavesdropper can pick up the key and break the code. Okay, I'll show some slides now. Here we have, in this illustration, we have Bob sending messages to Alice, but the way I actually coded it, Alice is sending the messages to Bob. And you have the eavesdropper, Darth, reading the key. So the scheme for secure key distribution, quantum key distribution, and by the way, this is a technology that is actually commercial. There are companies that are performing quantum key distribution and apparently making money off of it. So here's how it works. You have the signal, a binary signal, just zeros and ones. Now, any message can be encoded in binary, so that's no limitation. Then you have a polarizer. Now, what is polarized light? Well, I'm going to play a short video.
Do with polarization. So what exactly is polarization? Well, light is an electromagnetic wave, and so it has an electric component that oscillates, that goes up, comes back down, and keeps doing that as it moves through time and also as it moves through space. But it's electromagnetic, so it's got this electric component, but it also has a magnetic component, and this does the same thing. It oscillates up and down and back. Now, they go together, and so we have they go together in a very particular way. In fact, the magnetic component is exactly perpendicular at right angles to the electric component. So it looks something like this as it's going through space. So you can see the magnetic and electric fields oscillate together, and they're out of phase. So this light is linearly polarized because the electric field just goes in one direction. It goes straight up and down. Now, if we're say like this, that's going to be vertical polarization. And we move it this way, we call that horizontal polarization.
And there are also diagonal polarizations where it's a 45-degree angle halfway between vertical and horizontal. And these are these ways that Alice sends her signal.
Now, light doesn't have to be just vertically polarized or just horizontally polarized. It can be anywhere in between. Light sources that produce light that's polarized all over the place is what we call unpolarized light. So this is a flashlight, and it's going to produce unpolarized light. And I can demonstrate this for you by using a polarizer. So this polarizer here is labeled axes, and it has a little arrow, and that shows you which way it lets through, or which polarization it lets through it. So the first thing you notice is that this is somewhat dimmer than the backgrounds, and that's because it's not letting all the light through it. It's only letting the light that's polarized, in this case, with the electric field horizontal. So if we look at our light source through this, it's dimmer, but it's still there. Now we can rotate it around, and again, light's still getting through. So we have light that's getting through that's both vertically polarized, horizontally polarized, and everywhere in between. Now, if we expand this and we take another polarizer, it's just the same. Again, now we've got the axis horizontal. We can have light pass through one polarizer and then the other one. So if we put them this way, you see all of the light gets through. And that's because after it goes through this one, it's horizontally polarized, and that horizontally polarized light gets through, makes through the second one. Now, if we rotate these so that one of them is perpendicular to the other one, now all of a sudden, no light's getting through. And that's because the light that comes through this one first.
And you may have noticed that when he had it at a 45-degree angle, half of the light got through. Now, what light is it's a stream of particles called photons. And in this quantum key distribution scheme, you actually use single photons. And so if the polarizers are at a 45-degree angle to one another, then the photon has a 50% chance of getting through and a 50% chance of being absorbed.
First, to show you how these are set up like that, is all horizontally polarized, but this one only lets through vertically polarized light. So as a result, no light gets through. Do this with our
And are you on mute?
No. Can you hear me now?
Yes, we can. Thank you.
So Alice has a polarizer, and sometimes she orients it vertically, sometimes horizontally, sometimes at a 45-degree angle. And it's random. So she has a random number generator, which tell her which angle to orient the polarizer. You remember in the video, he had those filters and he was rotating them. And that's what Alice does. Of course, she does it electronically, not mechanically, which can be accomplished with voltages applied to special crystals. So there are actually 4 cases that you can have, because she can orient the polarizer vertically, and the photon might be vertical or it might be horizontal. If it's horizontal, it won't get through. If the random bit is 1, she'll orient the polarizer at a 45-degree angle. And again, half the photons will get through and half of them won't. The photons then go on to Bob, who has another polarizer that he orients at random, sometimes vertically, sometimes horizontally. And sometimes the photon gets through and sometimes it doesn't. So he gets a 0 sometimes, and he gets a 1 sometimes. And this is the way the communication is done. And the trick is that if Darth, the eavesdropper, were intercepting the photons, it would change their polarization, basically randomizing them. And Alice and Bob would be able to tell that there was an eavesdropper or someone modifying the message. Are there any questions or comments?
I don't see any, Anna. Is it okay to pause you for the questions, or you want to have the questions at the very end?
Oh, no, we can have questions now. Are there any questions?
No, no questions yet.
Okay. So here's the scheme. Alice composes a message. She transmits it. Alice and Bob compare notes, and I'll give the details about how they make this decision. And they can determine whether or not there was an eavesdropper or whether or not someone was modifying the message. If they determine that there was no eavesdropper, then Bob believes the message. If on the other hand, there's disagreement in the numbers that they get, then they just abort the communication. So this is basically, it's a way of being sure that there's no eavesdropper. Now, the scheme is a little bit complicated, and I simulated it in software to make sure I understood it and to make sure that the scheme really worked. So here's Alice's message. It's a binary stream of bits. She has a random number generator generating zeros and ones. If she gets a 0, she orients her polarizer vertically. If she gets a 1, she orients the polarizer diagonally. So you get R is for rectilinear. It means vertical and horizontal. And so, for instance, here, she sent a vertically polarized photon, and her polarizer was also vertical, and so the photon got through unchanged. In this case, she sent a horizontally polarized photon, and so the information got through. We got a horizontally polarized photon. But in some cases, she had the polarizers diagonal. And what that does is, remember when there's a 45-degree angle, there's a 50-50 chance whether the photon gets through or not. And that's what I've indicated with these asterisks. It's a wild card. It could be 0, it could be 1. So this is how Bob sets his polarizer: vertical, vertical, diagonal, diagonal, vertical and horizontal, diagonal. And so when Bob's polarizer agrees with Alice's, then he gets the same bit that Alice sent. But when his polarizer, for instance here, Alice was rectilinear, vertical and horizontal, Bob was diagonal, so he gets a random result indicated by the asterisk. And what they do is, Bob simply tells Alice in a public channel, not in secret, how he oriented his polarizer. Alice looks at how she oriented her polarizer, and she says, okay, for this one, and this one, and this one, and this one, and so on, my polarizer was oriented the same way as yours. And what that means is they should share information. They should get the same bit out. So what Bob does is he sacrifices some information. He publicly reveals some of his bits. And Alice checks to see if they match what she sent. And I'm showing the case here where there's no eavesdropper. And so K is okay, in other words, that they matched. So in this scenario that I've shown here, there's no eavesdropper. And what that says is the remaining bits, which were not revealed, were securely transmitted, and there was no eavesdropper. Are there any questions or comments?
Hey, Anna, starting with your second bit and relative to the bits received by Bob line, you have some that are missing. Is that, what does that mean, or is that just a typo?
No, that's a great question, Ron. That's attenuation. When I ran the simulation, I deliberately sacrificed a certain percentage of the photons. This table is based on the paper, which Taposh is going to post a link to the paper, and they modeled it that way too. You have an imperfect device and you have an imperfect fiber optic cable. Great question.
So if there was no noise, that second column should result in a 0 at Bob's end.
If there was no attenuation, if no photons were lost, then there'd be a
Great.
0 here.
All right, thanks.
Sure. Any other questions? Okay, now I think
Anna, there's one question from Nikki, and the question is, how many bits are needed to be revealed by Bob and confirmed by Alice?
well, you need a lot more than we've shown here, that's for sure. Alice is only confirming 3 of them. So that could happen one time in 8 just by coincidence. So you need, if you want a certainty of, say, an error rate of 1 in 1,000, you would need 10 bits to be revealed. And so the message would have to be much longer. That's another good question.
Yeah. And this is from my side now, do they use any statistical significance for this basically to make sure that they get it back, the original message?
Yes, there are formulas for the confidence level that you have that there was no eavesdropper. I don't have those formulas to show you, but it's basically based on powers of 2.
Got it. Thank you. Good question, Nikki.
Now I'm going to show you how I generated this table. Oh no, that's not the one. having a little difficulty getting getting it to share the code. Just a moment.
Sure. Meanwhile, while Anna does that, I shared the paper. So if people are interested, you can click on the link.
So I used Python and NumPy. What this seed is, with computers, there are no truly random numbers. And so you have a seed that causes the pseudo-random sequence to be repeatable. Now, by the way, there's a company, Quantinuum, they make quantum computers, and they have a service whereby they generate truly random numbers based on quantum mechanics, just like the random chance of a photon getting through when the polarizers are at 45-degree angles. But for the simulation, we're using pseudo-random numbers.
Thank you for that.
So I have a flag here, whether or not there's an eavesdropper. I'm going to show that if the eavesdropper knows what orientations Alice was using for her polarizer, then the eavesdropper can't be detected. So it depends on Alice keeping her polarizer settings secret. This function just produces a random bit. This produces an array of random bits. The bases are either rectilinear, that is vertical and horizontal. There are two quantum states, vertically polarized and horizontally polarized, and they're orthogonal to one another, so that if you have a vertical photon, there's zero chance of it getting through a horizontal, and vice versa. Likewise, there are two diagonal polarizations. You can think of them as like northwest to southeast and northeast to southwest. So I have R for rectilinear, D for diagonal. The polarizations, this is horizontal, this is vertical. This is like north, east, southwest. I couldn't get it to render a backslash, so I have an L for northwest to southeast. It just gets the polarization. Here's Alice's photon generator. She picks the random polarizations and then generates the photons. And one of the things I'm going to show is that if there's an error, if Alice's photon generator is imperfect, then they can't really tell if there was an eavesdropper or not. And this is a limitation of this protocol. This is the original quantum key distribution protocol that was published in 1984. There are better protocols where they're called device independent, where Alice's photon generator doesn't have to be perfect. But for this is the classic protocol. It's the simplest one. And for it to work, her generator has to be perfect. Now this lines 36 through 53 is the heart of quantum mechanics. This is a quantum measurement. So for instance, if we have diagonal polarization and we measure it in a diagonal basis, then the outcome is certain. But if we have a diagonally polarized photon and a vertical polarizer, then the outcome is 50-50 random. So there are 8 cases, and I just enumerated them all. So this is where the quantum mechanics get simulated. Are there any questions or comments?
There is one question from Barry. Barry, do you want me to read aloud or you want to ask it?
Well, I can read it aloud.
Okay.
But to what extent are physicists certain that the measurements of qubits in uniform superposition are truly random?
Well, the Nobel Prize this year was for measurements of polarized photons, and they analyzed the statistics to 1 part in a million or something. So it's pretty certain that they're random.
Gotcha.
If I understood the question.
No, I think that you understood the question and answered it. Thank you.
Okay, Barry. Any other questions? Here's a utility function that just simply shows the bits in that table that I illustrated. Test case, if this flag is true, these are the values that were used in the original BB84 paper. So I had to do that one first to make sure that I got the same table that the paper showed. But I also ran it, and I think the one I showed you wasn't the test case from the paper, it was random bits. Here I check if the eavesdropper knows Alice's polarization settings, in which case the eavesdropper simply, these are called bases. In quantum mechanics, it's all based on linear algebra. And in linear algebra, you have what are called bases. There's one element in the basis. Well, if you have 4 qubits, for example, the basis has 2 to the 4th power, 16. There are 16 bases. For 1 qubit, there are only 2 bases. And so what this physically corresponds to is, remember in the video, that guy was rotating the Polaroid filter. That's choosing a basis. Are there any questions or comments about bases?
No question on the basis.
Here's where I simulate the loss of photons. I use sets. A set is a Python data structure it's like a list, except for that there are no duplicates. And so I simply subtract. You may remember that someone pointed out that there was data missing for the second bit. Since Python starts numbering at 0, the second bit is index 1, and that's what this 1 right here removes that photon. And so I just take the intersection to simulate the successful transmission. Here's where Alice and Bob compare notes on what bases they were using. Now, my measurement function, if the outcome is uncertain, it returns something called none, which is a special data value. But for display purposes, I use an asterisk to indicate a wildcard. I think that's enough code, unless are there any questions about the code?
No questions yet about the code, Anna.
Okay. Now, in this case, there is an eavesdropper. And what happens is when Bob reveals, when he sacrifices certain bits of information for validation purposes, one of them is random because his basis was 45 degrees from Alice's basis. His polarizer was 45 degrees from Alice's polarizer. Let me get my laser pointer here. Right here. So half the time you'd get a disagreement here, half the time you'd get an agreement. That's not very reliable. As someone asked about, you really need a lot more bits to really be confident that there was no eavesdropping. But here's what happens with the eavesdropper. Bob's output, the message Bob gets after he decodes it, all these X's indicate disagreement, where Bob's bit is different from what Alice actually sent. Now, if the eavesdropper knows what settings Alice was using for her polarizer, then they can simply measure, they can just orient their polarizer the same way Alice oriented hers. In other words, measuring in the same basis. And in quantum mechanics, if you know the basis in advance, then the measurement is not uncertain. The uncertainty principle doesn't apply. And so when Alice and Bob compare notes, they get okay for all 3 revealed bits. And if there were 10, they'd get okay for all 10, and so on. So basically what this says is that if Alice's polarizer settings are compromised, then there's no security. You simply don't know. The eavesdropper is undetected. Are there any questions or comments?
None yet.
The next thing I did was I simulated errors in Alice's photon generator. make photons is Alice's photon generator. Well, apparently this code doesn't have the errors, but here it is. I simply add a constant to the angle. The polarizations here are the angles of Alice's polarizer, the orientation. 0 is vertical, 90 is horizontal, 45 and 135 are diagonal. And to simulate an imperfection in Alice's photon generator, I simply add a constant value right here to the polarization. Then when I perform the measurement, there is uncertainty. Even if Alice was trying to set her polarizer vertical and Bob was setting his vertical, sometimes the photons don't agree. They don't get through when they should, or they do get through when they shouldn't. So what happens is Bob reveals some bits. Alice checks to see if the bits she sent agree with what Bob received. And we've got an X here because what Bob got was different from what Alice sent. Alice sent a 0, Bob got a 1. So what this says is that if Alice's photon generator is imperfect, then you can't tell whether there was an eavesdropper or whether there was a defect in Alice's photon generator. And a lot of research is done, and this could be a topic of a future meetup, for protocols, which are what are called device-independent protocols. And what that means is that the success of the scheme is independent of errors in the photon generator or in the measurement. Now, it's not totally independent. There's a threshold. And if the errors are below a certain threshold, then you can compute a high probability that you know whether there was an eavesdropper or not. Are there any questions or comments?
No questions or comments yet.
Now, I'm just going to say a few words about another topic because it's something we're all interested in. This is the other branch of quantum cryptography, and I'm just going to say a few words about it. But all your email and your internet bank transactions are based on what's called asymmetric encryption, public key cryptography. And the way that works is if you have a large number that's the product of 2 primes, it's very hard to find out what the prime numbers are. A prime number it's a generalization of the concept of an odd number. Like 61, it's not 5 times anything, it's not 7 times anything, it's not 11 times anything. It's indivisible. That's a prime. And Peter Shor worked out a way to use quantum computers to solve this problem. so that when quantum computers come online, all your bank transactions and all your emails will be readable. And that's the reason why the National Institute of Standards held a competition over the past few years to come up with new encryption algorithms that can't be cracked, well, supposedly can't be cracked by quantum computers. I'm a little skeptical because I don't think we really know the limitations of quantum computers. So that was kind of a whirlwind explanation. Are there any questions or comments?
No.
And that completes the presentation. And I think Taposh has prepared some discussion topics.
Yeah. First of all, thank you, Anna. This was very interesting, and I really appreciate you showing us the source code as well. So thank you for that. I'm sure the participants would have understood how the basics of BB8 is. I'm going to ask one question just to prime the pump here. There has been a lot of work done on the QKD side. So I know there are a lot of other algorithms being published since then, since the BB884. Do you know what is the current state today? And would like to talk about some things there. Who's the leader in this area today? It's for your point of view.
That's a great question, but unfortunately, I don't know.
Okay. No worries. Anybody else wants to ask a question on QKD or opportunities in this area? Okay, I'm not hearing anyone. I'm gonna just ask you then. What are the potential opportunities that you see, and where do you see the future gonna be with this?
Well, we need repeaters.
Hmm.
We need a way to, because a photon in a fiber optic cable, it might get 50 kilometers, but it's not going to get from Chicago to San Francisco. Its chances of surviving that journey are very low. So we need repeaters. And the repeaters depend on something called Bell analyzers, which are combinations of polarizers and phase shifters. A phase shifter is a special crystal. It takes the index of refraction, that is the way it transmits light, depends on the polarization. And so it changes the polarization. And my understanding is that Bell state analyzers are not really a solved problem yet. And so this is where we have to go. We have to have quantum repeaters. We want a quantum internet, and we need repeaters to do that.
No, thank you. I think IEEE last year had in their conference had a section on the quantum internet, total section, and I was fortunate to attend that, and I could see like almost 25 to 30 papers in that, the high quality papers in that area. Another question, I think this would help some of our participants as well, is if somebody wants to start learning about quantum cryptography, what would be your recommendation?
I can send you my code.
Yeah, but is there any books other than that? I mean, I know one paper that we shared. Are there any other materials that they can look into to get started?
I would expect IBM on their quantum experience would probably have some pretty good resources. They're the leaders as far as being there for people who want to learn quantum computing. IBM is the leader.
Got it. Okay. I'm going to open it up for anyone to unmute themselves and ask questions right now. Anybody has questions? check. Okay.
So
Yeah, I
for
see
those
Kevin.
that don't know, Sandbox AQ just got $500 million to do these types of things on conventional hardware. So it's going to be a huge thing. So you can defend on a classical computer if you get attacked by a quantum computer. So we'll see where that funding goes. But that's the number one thing I would say right now for quantum is cybersecurity.
Mhm. Thanks, Kevin. It's a good ad.
I was going to add something to the what should you learn if you're interested in quantum cryptography. You might want to make sure you have a good understanding of classical cryptography
Oh, yeah.
and effectively the Bible on that, which is actually it's a pretty old book called Applied Cryptography by Bruce Schneer.
Okay.
I love to promote this book because I worked with Bruce back in the early 90s.
Oh, nice.
And I've reached out to him a few times, but now he has an agent and he's just too famous for normal people. But his book is basically the Bible on cryptography, and it's all fairly current still. I mean, there have probably been some incremental improvements in cryptography over the years, but if you want to learn the basics, that's the book. And get a handle on the classics, and then tackle the quantum side.
Thank you, Ron.
Well, the one-time pad is like really, really fundamental. If you don't understand what a one-time pad
Mhm.
does for you and what the issues are with using them, that's really the starting point.
Got it.
And that's explained in Stallings' book on network security as well.
Yep, Stalin's book has been around for some time now. I remember reading it in school, grad school. Yeah, it's been a
Well, he
while.
keeps coming out with new editions.
Yep. You need to be, so I need to keep up, basically. Okay. Okay.
Yeah. So
Yeah, go ahead.
besides all so you have NSA and the NIST algorithms coming through. There's also, if you look on ISO and IEC's website, there's two quantum standards about to pass. They're in I think that they call it like a 40.6 out of 90, but those go through. Now also late last year, so December, there's now a law that all federal agencies must start to implement some sort of quantum defense, and I believe it's by the summer. So between the standards and then the White House, this new law, and then NIST and NSA, you'll start to see, this story unfold where who knows, maybe by the end of this year or next year, more consumers starting to do PQC on their laptops.
That's a big change. Yeah. And are there already software companies because installing it includes a lot more logistics, right? Or is it going to be like centrally administered? Is there any talk about that? Are you aware of that, Kevin?
That I'm not sure. I know there's a ton doing, quantum internet, and if it's not pure quantum internet, it's entangled internet, which isn't as technically as hard. I think Aliro kind of leads all that. I don't know what the setup will be on, personal computers, if it can be done, in the cloud, that type of stuff. But yeah, it's to be seen. As far as the hardware requirements, not sure either.
Quantinuum has an offering. They have a product called Quantum Origins, which does post-quantum cryptography.
Yeah, so you can get keys made at Quantinuum. That's a big thing of theirs. It's based on quantum computers being inherently noisy. So, it's a service that they own.
Nice. Yeah, maybe we should invite Continuum once to speak to us here in this group and see what they have.
Yes, we should.
Yeah, I was looking at
Um,
it for a project, and basically you can't, so if you want to do an experiment based on entropy, it's really hard to measure the end of it. The only thing you can prove is your techniques or your methods leaning up to your final whatever. So say for instance, Quantinuum's, software approach, with, getting a key is, they think, is a lot more secure than a random noise generator, a quantum random noise generator that's in these, Samsung Galaxy phones overseas.
Mhm.
Because it would take many, many supercomputers just to, classical supercomputers to analyze the output to prove that your entropy, using a specific service compared to others is better, if you were to quantify it.
Yeah.
Yeah, you've got to make good random numbers, you need a lot of entropy. And this is a problem because like for routers and modems and switches, they don't have a lot of entropy. And when they generate their asymmetric keys, their public keys, they have a tendency to have prime factors in common. And if you have two asymmetric keys with a prime factor in common, all you have to do is compute the greatest common divisor, which is a very quick calculation, and you've broken both of those keys. So that's an issue. Not for big computers, maybe not even for laptops, but for routers and switches and
Mhm.
some of the smaller appliances, it's a problem.
Well,
I
we'll see what future entails.
I was going to say that the Washington D.C. group a month or two ago had a lady from Quantinuum come talk about Ticket, their software stack for
Oh,
their product. I believe her name is Katrin Spendier.
okay.
You can find her on the Washington D.C. meetup page and watch their YouTube recording.
Perfect. Perfect. Thank you, Ron, for sharing that. Appreciate it.
Yeah,
Also
there's
wanted to talk about, you're talking about, is quantum key distribution going to become a thing, and the issue of repeaters. If the alleged success by the Chinese of their satellite network,
Mhm.
and my understanding of that and it may be flawed, is that the satellites don't participate in the communication. Their whole purpose in life is to generate entangled pairs of photons and send them to different points on the planet. And they claim that this is happening, that they're doing this. When you really get into looking at what they're doing, it turns out they have to send somewhere in the millions of photons to get a single pair of properly entangled ones that are usable. And I don't understand the reason for that, but it comes down to being somewhat slow. But then again, all you're doing is generating keys. So even if it's slow, it might not take too long to generate, 2000 bits.
Mhm.
So, but if what they've alleged is true, that will probably become the future of quantum key distribution.
Yeah, another key company with all of this is called ID Quantique. So they're based in, I think, Geneva, and they've been around just as long as, say, D-Wave, 20 something years. And they have like an array of services, for quantum security, QKD, PQC, the servers. I think they're the ones that actually supplies the chips to the Samsung Galaxy phones. So overseas they call them the Samsung Galaxy Quantum whatevers, but they're really just random number generators, like a small chip that uses some effects of quantum mechanics. And yeah, if you check out their site, it's just ID Quantique.
I
It's,
see one day.
they're definitely have been leading it for a while.
Thank you. That's good piece of information. I'll check out their site. Really, really appreciate everyone. I think we are at time right now. So really appreciate everybody for your contribution. And thanks a lot, Anna, for coming and speaking to us. Uh, thank you. Bye, everyone.
Yes,
Thank you, Anna. Appreciate it.
You're welcome.